Modern electronic hardware is densely packed, and every trace and wire acts as an unintended antenna, radiating chaotic, invisible electromagnetic energy into the surrounding space. If you fail to control these fields, your product will fail commercial or military emissions tests, bringing development to a grinding halt. To fix electromagnetic interference, or EMI, you have to understand that it always requires three distinct elements to exist: a source, a coupling channel, and a receptor. The source is the component generating the noise, often a switching power supply, a fast digital clock, or a motor. The receptor is the susceptible circuit that is malfunctioning because it's picking up that noise. In many designs, you can't swap out the power supply or redesign the sensitive receiver logic. That leaves only one option: attacking the coupling channel. But the coupling channel is literally empty space. Trying to map out a three-dimensional wire harness using Maxwell's equations across three spatial dimensions and time is analytically impossible for most real-world problems. We can bypass that complex math using a specific approximation. As long as the physical dimensions of the circuits are small compared to the wavelength of the noise, we can model the empty space as a lumped component network, replacing invisible fields with standard schematic components. Today, we are focusing on how time-varying electric fields bridge the gap between circuits, a mechanism known as capacitive coupling. By translating complex spatial geometry into standard circuit parameters, we can mathematically dictate exactly how to break that noise channel. Consider two parallel wires side by side. When a time-varying electric field emanates from conductor 1, it interacts directly with conductor 2. We can translate these physical wires directly into an equivalent lumped network schematic to see exactly what is happening. The electric field coupling the two conductors is represented by a mutual stray capacitance, C12. Each individual conductor also has its own stray capacitance to the system ground, defined as C1G and C2G. The active interference signal on conductor 1 acts as our noise voltage source, V1. Finally, conductor 2 is connected to some actual circuitry, which provides a defined resistance to ground, denoted as R. The invisible electric field has now been fully captured as a simple, closed-loop schematic that we can evaluate using basic AC circuit analysis. Solving for the induced noise voltage Vn gives a complete transfer function. Because physical circuit resistance R is usually smaller than the stray capacitance's high impedance, we simplify the denominator. This leaves the primary governing equation: Vn equals j omega times R times C12 times V1. The math shows direct proportionality. To lower the noise on your receptor, you have to lower the frequency, lower the aggressor's voltage, lower the receptor's circuit's resistance, or lower the mutual capacitance. This chart plots the frequency response. Induced noise voltage increases linearly as angular frequency goes up, but at incredibly high frequencies, the curve hits a hard ceiling. Here, maximum noise is determined purely by the capacitive voltage divider formed by C12 and C2G. In reality, you usually can't change the operating frequency or the voltage of the source without breaking the product. That leaves engineers with only two functional levers to pull: reducing the receptor's circuit impedance or physically attacking the mutual capacitance, C12. This graph shows conductor spacing versus mutual capacitance. Moving wires apart causes an initial rapid drop in coupling, but look at the long tail. Once separation reaches 40 times the wire diameter, the curve flatlines. Beyond that, adding space provides almost zero additional attenuation. Modern hardware is constrained by tight enclosures and dense printed circuit boards. We rarely have the luxury of routing cables inches apart to chase diminishing returns. Because physical separation alone cannot completely eliminate mutual capacitance, we have to introduce physical barriers to actively break the coupling channel. The standard engineering instinct is to fix capacitive coupling by wrapping the susceptible line in a physical copper shield. But what happens mathematically if the shield is just laid over the wire and left unconnected, or floating? We can derive the answer by looking at the equivalent circuit. The metal barrier physically splits the original mutual capacitance into two new capacitors in series: C1s from the aggressor to the shield, and CS2 from the shield to the receptor. Because the floating shield has no electrical path to ground, it acts as a highly efficient intermediate node in a capacitive voltage divider. The electric field couples across C1s, and the floating shield picks up the interference voltage. The circuit behavior is consistent. The shield re-radiates that exact voltage to the inner conductor, resulting in a noise voltage equal to the shield voltage itself. The ungrounded shield accomplished absolutely nothing to protect the circuit. It just passed the noise right through. The mathematical solution, then, is to actively ground the shield. By establishing a low-impedance connection to the chassis, you force the shield voltage to 0 volts. With the shield held at 0, the first capacitor is completely decoupled from the second, entirely breaking the noise channel. While EMC involves complex variables, the lumped component model provides a predictable basis for shielding decisions. By translating invisible near-field radiation into schematic parameters, we demonstrate precisely why certain physical configurations fail and implement verified methods to break the coupling path.